Okay, we continue the study of metric spaces again in this video. Last time we gave one example of a metric space, precisely the absolute value function on a set of real numbers. So today we move our discussion and then take more examples so that we get more familiar with the notion of metric spaces. Precisely, we want to, the more examples we do, the more we learn how to show that a given function is a metric. So we have this. Let X be R2, the Euclidean space. By R2, we mean R cross R. I believe anyone watching this video is not going to have a challenge with this because I've taken time to explain what we mean by Cartesian product of a set with itself. So let's define D1. I name one not because of any, just to differentiate from other functions I'm going to give. So I define D1 from X cross X into R by D1 of X comma Y is summation, absolute value of Xi minus Yi, I going from 1 to 2. This is compactly written, so I can explicitly write this as absolute value of X1 minus Y1 plus absolute value of X2 minus Y2. So if I define this function D1 in this form, then the claim is that D1 is a metric on capital X. Okay? And we want to prove that D1 is a metric on X. So it suffices, to show that D1 satisfies A1, A2, and A3 in the definition of a metric we gave in the previous video. Alright. For D1, for A1, sorry, let's take X, Y, and capital X. Arbitrary, okay? What does it mean? This means, so X in capital X means I can write X in the form X1, X2 with X1 a real number and then X2 is also a real number. Similarly, Y belongs to capital X means that I can write Y in the form Y1, Y2 with Y1 a real number and then Y2 also a real number. This is what it is. Now, notice that, or remember that for any real number, the absolute value of A is always bigger than or equal to 0. So with this now, we have that absolute value of X1 minus Y1 is non-negative. Absolute value of X2 minus Y2 is also non-negative. Because X1 is a real number, X2 is also a real number. Y1 is a real number and Y2 is a real number. Therefore, X1 minus Y1 is one real number. So we can apply this, and then if we do, we have absolute value of X1 minus Y1 is non-negative, and so this is also non-negative. If we combine this together, we have that the sum of X1 minus Y1 and X2 minus Y2 is non-negative. And that says that D1 of X comma Y is non-negative. Alright. To complete verifying condition A1, we need to show that D1 of X comma Y is 0 if and only if x is equal to y. But this is not challenging too, because d1 of x comma y is 0 if and only if the sum, absolute value of x1 or xi minus yi, I from 1 to 2 is equal to 0. And this is true if and only if individual terms of this sum is equal to 0, because individual term in this sum is non-negative. So with this, we can conclude immediately that absolute value of xi minus yi is equal to 0. And so we have absolute value of xi minus yi is 0. Here I is 1, 2. I is 1, 2. And from here we get that xi is equal to yi. I equal 1, 2. And that is x is equal to y. So we have seen that, or have shown that d1 of x comma y is 0 if and only if x is equal to y. So combining this with what we did before, we'll conclude that A1 is satisfied. For A2, this is also simple. We take x and y in capital X. Again, we take it arbitrary. D1 of x comma y by definition is sum absolute value of xi minus yi, I from 1 to 2. This we can write as summation I from 1 to 2, absolute value of minus yi minus xi, and then this is the same as sum I from 1 to 2, absolute value of negative 1 dot absolute value of yi minus xi. Absolute value of minus 1 is 1. So when you multiply, you get just this piece. So this becomes summation I from 1 to 2, absolute value of yi minus xi. By definition, this is nothing but d1 of y comma x. So what we have done is we've shown that d1 of x comma y is the same as d1 of y comma x, concluding the proof of A2. For A3, we take x, y, z in capital X, arbitrary, and so we compute d1 of x comma y. Our goal is to show that this is less than or equal to, so our goal is to prove that this is less than or equal to d1 of x comma z plus d1 of z comma y. So I put a question mark here because that's what we want to do. Okay. If we compute d1 of x comma y, by definition this is sum absolute value of xi minus yi, I from 1 to 2. We can write this as summation I from 1 to 2, absolute value of xi minus zi plus zi minus yi. Please be guided that all these variables are dummies, so you are free to choose any of the letters of the alphabet to stand for your elements. Okay? So with this now, recalling that absolute value of a plus b is less than or equal to absolute value of a plus the absolute value of b. That's the triangle inequality for the absolute value function. If we use this here, we're going to have from here that this is less than or equal to summation I from 1 to 2 of absolute value of xi minus zi plus absolute value of zi minus yi. This is the finite sum, so we can move the sum inside. So this is the same as summation I from 1 to 2, absolute value of xi minus zi plus summation I from 1 to 2, absolute value of zi minus yi. Good. For conclusion, we have shown that d1 of x comma y is less than or equal to summation absolute value of xi minus ci I from 1 to 2 plus sum I from 1 to 2 absolute value of zi minus yi. Who is this and who is this? This is nothing but d1 of x comma z plus d1 of z comma y. And that's what we need. That is, i.e., d1 of x comma y is less than or equal to d1 of x comma z plus d1 of z comma y. So d1 satisfies, since d1 satisfies a1, a2, and a3, means that d1 is a metric on x. Hence, x together with d1 is a metric space.